a couple of things that I'm going to go over based upon, I got a bunch of emails, and so I tried to sort of combine a little bit of everything. One of the first questions that really surprised me, how many people struggle with this, because again, the quizzes are not supposed to be hard, and yet this question ended up really screwing a lot of people up, even though I didn't mean it to screw you guys up at all. But I'll just tell you, we'll go sort of through this. All right, so the question here is basically a question of reversible nature. I think for one quiz, I think I asked for the mechanism of this, maybe. And then for another quiz, so certainly you should be able to show the mechanism of this, just catalyzed by, say, acid or something like that. The other question was sort of which way will the sort of equilibrium lie in a problem like this? And certainly when I ask a question where I'm asking the equilibrium which way to lie and why, and especially a question like this, where in principle you could answer the question one of two ways, either of which could be supported, and either of those of which I would have given complete credit to. But what I'm not going to give credit to is somebody simply circling an answer and saying it's this one, especially when either one of these could in principle be the correct answer depending upon how you answer it. Now, when looking at a problem like this, I would hope that by this point all of you guys would sort of recognize that there's sort of one critical feature that you should sort of redraw these into at first, right? That would be to put these into a chair, okay? Now, when you put these guys into a chair, right, you're going to have this sort of six-membered oxygen-containing ring. And as is drawn right here, I basically have this position here as that group there, okay? Now, I don't know if this was one of the problems that people got into initially, but again, as you guys learned last semester, you shouldn't be forgetting what you learned previously. The whole reason why I put this isopropyl group here was to lock this molecule into a specific conformation. And that conformation would be one such that the isopropyl group is going to be equatorial. I had a ton of quizzes where people were taking, and they were drawing this in the axial position, as if somehow the anomeric effect over here might then, ergo, cause some reason that this would want to be axial. I don't know if that was the reason or not, but that's what I was getting, is a lot of answers where this was drawn in the axial position. The moment that you do that, you can no longer answer this question because you've basically taken something that I assumed would be fairly straightforward and sort of change up on that. Okay, so in this case, if this is equatorial, right, this is going up, we've got a group here. It's going to be in one of those two positions. Where's the OH going to be? For the left one, right? And again, you can sort of think about this as looking down this way, right? We're sort of looking down the molecule here, we're looking down the molecule. The isopropyl group's coming towards you, and if you're looking at the molecule down this way, which one's going to come first? It's going to be the axial one, right? This is one chair. Right? The other chair would be the same thing, but now you will just have your OH. Okay? Now, based upon our lecture, what I was expecting you guys to say was, what did I tell you guys in lecture about enol ethers? That they... about hemiacetals in ring systems, sort of anomeric carbons with a hydroxyl, right? This is where you're going to have sort of anomeric effect argument. The oxygen may end up favoring the axial position, based upon an anomeric effect argument. So if you looked at both of these and said, okay, we have the anomeric carbon here, right? We have a hydroxyl there. I'm going to put that into the axial position due to anomeric effect argument. Then great, that was one potential argument. Now, because the book always throws a kink in all of my teaching plans, what the book also said, right, was that heavy acetals, they don't even bring up the anomeric effect. And they say it's going to be equatorial. And so if you instead said, it's this molecule, because both these groups are equatorial, then great. And I gave you full credit. So if you said this, and you said anomeric effect, great. If you said this, and you said both are equatorial, great. If you circled one and gave some answer that didn't make any sense, I didn't give you any points. So a lot of people are complaining about not getting any points on this. But the argument, again, you can't just circle one and expect to get 3 points and expect to project my rubric, especially in a question where either one of these could in principle be right. So this is a perfect example of where the rationale is more important than the argument. Or sorry, is more important than the specific answer. So again, this is fine if you answered anomeric effect. This is fine if you answered both are equatorial. Both of those I gave full credit. If a similar question comes up on an exam, again, as hopefully I've sort of made clear, as long as you are making arguments that are based upon real chemistry, I will consider that. And if you make an argument that makes sense based upon what I think a organic 2 level should be, and you've sort of used rationale in your argument, I will be generous in my grading. But you can't just expect to have, because you circled one that so did your friend did, that suddenly you get half the points. So that's that. Okay? All right, so now we can move on. All right, so that was the one thing that people wanted to go over. All right, so what we're going to focus on today is, I think, 2 things. So this is probably a good transition to one question that people had. So we've matured in terms of diastereoselectivity, right? We've matured from some of the sort of basic diastereoselectivity questions, such as, right, if you have a molecule like this and you treat it to bromine, right? This is sort of first semester organic chemistry, stereochemistry based question, right? If I take this molecule and I treat it to bromine, I'm going to get a certain diastereomer. What is that diastereomer? And again, if you get a question like this, sometimes it's best to go through looking in and out of the board. So what you can do is, if I rotate this up, right, we can sort of take this and put it in the plane. This sometimes makes it easier because now when you react with bromine, generate that bromonium ion. Right, and so this is sort of first semester organic chemistry, stereochemistry. It's I think a lot of your stuff from right, and so that would be your stereochemistry, right? So this is sort of a lot of where the stereochemistry comes up in organic chemistry 1. It's alkenes, it's cis dihydroxylations, right? It's trans-based addition of an alkene. It's of, say, bromine or bromine and methanol or something like that. Or, what's another one that you guys have seen? Eliminations, right? An E2 elimination. What's the resulting stereochemistry of that alkene going to be when we form it? And so when we sort of came to organic chemistry 2, I think that we had some a little bit more complex stereochemistry, particularly in the pericyclic-based processes, right? And one of them that I think relates certainly to what we might consider things like alkenes, right? Actually, it relates exactly to alkenes, right? Is Diels-Alder chemistry, right? So if you have a situation where you have an alkene, right, and you react it with, say, for example, cyclohexadiene, right? There is going to be stereochemistry, right? And a lot of times the stereochemistry that's going to be generated here is analogous to the syn addition of, say, for example, osmium tetroxide, right? So dihydroxylations, right? That sort of syn addition into that bond, right? Where the resulting product is going to have the methyl groups on the opposite sides of one another, right? And the protons on opposite sides of one another. So within a question like this, right, the first thing that you're going to be able to have to do is sort of recognize the Diels-Alder product. Oftentimes it's good to get in the habit of trying to draw it in sort of 3 dimensions. So what I've suggested to some of you is to sort of draw this, right, in sort of like a sort of that sort of syn-based orientation. Yes, Shimon. Yes. Yeah. So oh, sorry. Yeah. Sorry. Yeah, sorry about that. Yeah, so Diels-Alder, right? These are going to come together to undergo a Diels-Alder process, and in this reaction, sometimes it's easy to see in that way. But now when it's going to form, once you have that compound drawn in terms of this syn addition, right, what you're going to end up with is a molecule again, as you sort of push these around, what's going to happen is we're going to form a double bond there. We're going to form 2 bonds on the other sides. And then everything here is going to stay in place, right? So the proton I have currently going up, so the proton's going to go up. The methyl group's going down here. And then again, if you can sort of see that first position, then it should be fairly easy to then see the second position, right? Because the methyl group is going to be on the opposite face, right? So in this case now we have the methyl group coming up, and we have the other group going down. So again, in a situation like a Diels-Alder, it should feel very analogous to, I think, other alkenes that we've seen. Again, if we want to start talking about easy selectivity within here, we can do the same thing. You can draw it in this way and see it. So these are things that you should be able to do. Now, it goes a step further, right? I think when we begin to think about pericyclic reactions, where you have to invoke sort of low energy transition states. So somebody emailed me a question about steroid synthesis, and so I'll sort of mix these 2 together a little bit, just as a reminder. I'm just going to put PPP here. So that's the diphosphate, just to save space, right? Right? Now, one of the sort of syntheses of steroids, and one of the things that you should sort of recognize when we're sort of synthesizing steroids is that you can, again, it could be a little bit more complicated than this, but this is the general idea, is this alkene is going to attack. We're going to sort of lose that phosphate, that sort of pyrophosphate. That's what the PP stands for. It's dipyrophosphate. Okay, so what's going to happen here is we're going to end up getting a molecule . 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Make sure that all our carbons are there. Again, if you want to count them, sometimes you can count 4, 5, 6. So you see that methyl group showing up there. 1, 2, 3, 4, 5, 6, right? So we're making the 4-5 bond, and you see that what's left over is at 6 is we have that carbocation as well. And again, at this point, generally an elimination takes place. Many different eliminations can take place. I think some of the confusion often comes up that says, well, why can't I eliminate here or here? Well, it's an enzyme that's doing this, okay? So sort of the way that these processes take place are controlled by enzymatic processes, so they're not necessarily controlled by the same things that we consider in terms of Markovnikov, or sorry, Zaitsev's rule or whatever sort of global equilibrium. Again, these are controlled by enzymes, and so what's going to happen here is we're effectively going to get oftentimes an elimination in that position. Okay, and then we're going to sort of If we want to keep growing up on this, we could take a series of these and continue that process and start getting to molecules like squalene and so forth. Now, one of the things that I wanted to sort of bring up here, though, is that when you get to a situation like this, these molecules certainly cyclize, and they can cyclize, and we sort of saw this within steroids. And one of the ways that we can do this, and I think this is sort of important moving forward, especially anybody that's looking to take sort of more advanced courses in this. A lot of stereochemistry, and when we sort of compare this to some of the other reactions that we'll learn, the transition states can often be the sort of lowest energy transition states. Again, the sort of energy barrier is going to be lower in a lower energy transition state, and as we've sort of learned throughout the semester, chair conformations and six-membered rings represent one of the sort of lowest energy species that we can have, again, because all the angles are generally at the sort of preferred angles. But if we want to take this molecule and try to cyclize it, right, into that six-membered ring, sometimes it's difficult to simply take a molecule like this and just draw it right into the molecule itself. And so one of the things that I often will do is I will, especially if I'm going through a six-membered sort of chair-like transition state, is I'll start just by drawing a reference chair. Just so I can remember sort of what it looks like. And again, in this case, maybe the bond that I want to make is going to be this one here. So if I'm going to make this sort of 1,6, right, I can sort of think about the fact that at that sort of first carbon, we're going to have sort of two methyl groups, right? Sort of 6 carbon here is ultimately going to form the bond, so there's going to be probably a proton as well as another group there. But what we can begin to start doing, right, is sort of realizing that generally what happens is we're going to sort of oxidize, say for example, right, which we've seen in the past, forming a carbocation at that position, right, and then we have our other alkene that's going to be there, that's ultimately going to be the 5,6 again. So when we're sort of looking back, we realize that at the 5 carbon, you're still going to have a methyl group, and at the 6 carbon, you're going to have something coming off here like this. And when you look at this compound in general, there's a few things that you may sort of recognize, right? The first is the groups that we have in here, this is sort of the point that I want to make in here, is when we actually undergo this cyclization, the one that we're sort of seeing here, the groups are in specific positions, and based upon those positions they certainly have chair-like characteristics to them. So even though this isn't a straight chair, I've drawn it into this conformation that's very chair-like. And so a group like this, right, you can sort of be able to tell that this group going down, what does that sort of remind you of? Equatorial or axial? Right, so this sort of reminds you of an equatorial position, right? And again, just based upon that chair reference, right? If what we want to do is say, look, there's your equatorial, there's your axial and equatorial. This group over here, right, that looks like the equatorial one, right? And again, there would be a proton coming down that would be in that axial position. Now over on this other side, we're going to have a carbocation left over, so there's not necessarily going to be any of that characteristic to it, but if we were to sort of think about what might end up happening, it does have a feel to it that's very much axial as well, and so the chances are if something came and added in, it would probably add through the equatorial position as well. But again, once we draw this intermediate, after the bond is formed, it starts to take on this chair-like conformation. Right, so everything starts to take this sort of chair-based conformation. Again, we have a sort of cation left over. Yes, Mark? Well, we don't right now. There's nothing. It's a carbocation. But let me ask you a question. What would be the stereochemistry of that carbon? Or sorry, what would be the sort of geometry around that carbocation? Right, it's sort of going to be sp3. And perhaps the better question at that point is it's neither axial or equatorial at that point. But if now you're going to have a nucleophile add in, where do you think it's going to attack? I think it's, what's that? Yeah, I mean, you may have to like actually, so this is sort of something that we may need to actually get a model out to sort of actually confirm, but my intuition would tell me that the group, so I guess this isn't something we've discussed too much, so that would be probably an unfair question, but it's generally going to come from the sort of exocyclic phase. So to sort of come in and attack the carbocation from inside the ring might be challenging, right, because it's got to get by this methyl group and all that other stuff in there. So chances are the group's going to come from the outside. And again, if you think about when we're talking about equatorial versus axial, the axial is straight up and down. The equatorial is all the stuff that's coming around the outside. Again, it's like the equator, right? So if we're coming from the outside, then any group that's going to attack there is probably going to end up in the equatorial position. But again, all right, so that's simply to help somebody's question about sort of that. And again, if we wanted to extend this further, we could perhaps put another one up there. We went over this a little bit in lecture, so you can watch that again. But the same chair-based transition states come up in a lot of our other reactions as well. So let's discuss perhaps a reaction we haven't discussed yet, but we have in a way. And that's going to be a Cope reaction. Now again, the sort of challenge with the Cope reaction, right, is that oftentimes reactions like this, a reaction like this, so if I give you a problem like this and ask you to sort of tell me what the stereochemistry of the product would be, it would kind of be a silly question, right? Because in principle, the equilibrium is going to lie this way, right? So you can certainly predict what the other, what the sort of minor equilibrium component would be in this, but in principle it would go the other way. So let's just make it. Well, why would you? Well, why would you
know that the equilibrium is going this way?
What do you think?
Not the other way around.
Somebody answer Jamoke's question. I'm hearing. So what?
Oh, okay.
Yeah, so the more substituted double bond, so that's sort of like one of the things that seems to...
How do you know in the minor state?
We're going to do it. Okay, so, but I'm going to make it a better question now, okay? And I'm going to show a version that's called an oxycope, okay? So if I have an O minus there, or let's say an OH, this is, the other one was a cope, this is considered an oxycope. Okay, what's going to happen to that intermediate that I just drew there? All right, it's going to go from the enol into the keto tautomeric form. So via Le Chatelier's principle, you can drive this, even though this equilibrium will be small, the overall process gets driven towards the carbonyl. Okay? And again, because the carbonyls are more stable. So an oxycope is one way that you can drive cope rearrangements in instances like I've shown here, where we want to sort of look at the relative selectivity and stereochemistry here and sort of try to sort of see this. Okay, so that's how we drive it. Now the question that I really wanted to get at was, how do we predict the stereochemistry? And this was kind of a question that we had on the second exam, right? What's that?
A lot of questions.
No, just one. For this, there's one cope. Okay, so anyway, so you want to be able to do this question, just in case it comes up on the exam. And again, one of the things that you'll want to do here, right, is you can sort of certainly recognize that there's perhaps stereochemistry involved. I think when I wrote this type of question on the exam, I really wasn't meaning to address sort of stereochemistry, but we can take it up a notch and put stereochemistry there simply to, so that when we actually draw our chair transition state, we have something to find there. But again, based upon what I sort of said earlier, right, we have this six-membered ring, right? And the fact that we have this six-membered ring, we can now begin to think about this in terms of a sort of chair transition state. Okay? Now, yeah, that's the enol keto tautomer. Right? Yes, Margo.
But don't we use the stereochem in the, because it was kind of actually good.
We're not, yeah, we don't,
We're not in the
I don't care about the stereochemistry, I care about the stereochemistry.
Oh, okay.
Yeah, no, we're going to address the stereochemistry. But you're right, yeah, yeah. Okay, so again, one of the things that we can sort of do is begin to draw our sort of chair, right? Make this cyclohexane. Again, if you want to start, like I said before, again, I allow pencils on exams, so you could certainly do what I just did before, is say, okay, I just want to draw that chair just so that I have the chair conformation there, and then that's going to be the bond that I'm going to sort of form, right? And then what I'm going to have is I'm going to have two alkenes here and here, right? And then perhaps I'm going to start building from here, right? So let's say that this is going to be the alkene on the bottom, okay? As I have drawn here, this methyl group, I've got to put a methyl group either here or there, okay? It's either going to be axial or it's going to be equatorial. Pseudo-axial, pseudo-equatorial, right? Because it's the transition state. So this methyl group, if this methyl group is going to be this methyl group, which one's it going to be? Equatorial. Why? Right. I'm not simply putting equatorial here because equatorial is lower in energy. So I'm sure many of you will make that interpretation. It just so happens that I drew this one. That's trans. That's trans. That's the only reason that we drew it in that way. So proton up, Me down. Okay? Now, in the case that we have drawn here, we also have the sort of hydroxyl, right? In this transition state, the hydroxyl, as I've drawn, is sort of going up. Okay? And again, we can address that later on if we so happen to want to. Okay? But the other thing that we have is this other alkene over here. Okay? And again, same as before, if we sort of just imagine this being a sort of chair, we've got equatorial up, axial down. Right? Now we're talking about this alkene over here. And again, as is drawn, right, we are going to have this be trans, the same as we had before. Okay? And so again, here's one possible transition state. Okay? We could also, in this same conformation, this is where these types of questions become perhaps a little bit more complicated, because in fact we can sort of wrap this around the other way. But certainly one of the things that we can do, let's just sort of say we want to draw the sort of other form of this, right? What we can do is just draw the sort of pseudo chair flip, right? And now this one's going down, so that one is going to be that bond there, right? Okay, so that's ultimately what that one's going to look like, right? So if we sort of transpose this over here, right? Now again, what we're going to do, right, is now we've got this center here. But again, what are we going to have here? We're going to have this be trans, right? So we've got two options here, right? This carbon here is this carbon here, right? But again, based upon, we're not simply rotating around them. So all that's going to happen here, right, is that in this situation, the methyl group's going to be going up, right? Methyl group's going to be, trans. It was going up here, but again, because we've effectively rotated around that bond, again, we're not going to make a cis, we're not going to make an alkene go from cis to trans. That barrier is too high. But you'll notice if you simply do this chair flip, pseudo chair flip, not really a chair flip, but you see that we're still trans, and the same as that way. So again, we're still equatorial in this position, so it sort of becomes irrelevant. Again, we could try to draw it in the axial position, but as we sort of see here, we're not running into that problem. And now we've got this group here, right? Again, we've got two groups there. Again, which one is the methyl? Well, the methyl is going to be the one that's going to be trans here, right? And so it's going to be equatorial as well, right? And it just so happens that in this transition state, now we've got the OH over here, right? And so by sort of going through this iterative process, we've sort of taken a look at these two. Again, these are both effectively going to lead to the same product anyway, but at least we've gone through the process of drawing them. Now, could we try to draw this in a way where they're going to be axial? Yeah, no, I don't. I think it's difficult to do it, right? I think as I'm sort of looking at this, I'm struggling to see a way that we could draw any way other than bis equatorial, right? Because if you think about your standard chair conformation, if we think about what a chair conformation is, I often show people this when they're sort of getting into drawing chair conformations. Right? What a chair conformation really is a set of parallel lines, right? So you've got these sort of parallel lines here, and again, your sort of equatorial is sort of anti to those, right? You've got a set of parallel lines here, right? And again, exactly anti to those is this one here, right? That's anti, right? That's anti. Right, and then this is anti over here, right, and so this is parallel with that, right, so you can sort of see this parallel nature built within these. Again, we have the white bonds here, right, those are here and there, so we see, again, anti, anti, right, and so really, when you think about it, all the sort of equatorial bonds are kind of anti to one of the bonds in the ring. So if you've got a sort of a trans double bond, I guess it would be difficult then to draw that trans double bond any way other than equatorial, right? And then obviously I don't have any other colors in here because I have purple, but then you have the up and down ones that are, right? And these are all anti to one another as well. So, so again, when you start thinking about the trans, well, you know, it's really the bonds here. This is trans with that, this is trans with that, likewise all the way around. So anyway, so I guess it makes it difficult, but, or rather, I don't want to say difficult, but it makes it not possible. Okay, so now when we're looking at this, now we can draw the product and we can sort of keep it within this chair conformation, right? So again, given the option of these two, I guess we'll go through this intermediate because we've got the OH equatorial. Where it may end up mattering is in a problem like we had in the, and maybe I'll sort of get back to this in a moment, where it may end up mattering is the stereochemistry here as it did on the exam. Let's go ahead and do this. Okay, so let's use our color coordination to follow what we've done, right? So this is where we're forming that double bond there, right? And then we're going to have equatorial methyl group. Right? And then over here we have in sort of the green, right? And so what we see here is that the molecule that we've effectively drawn is one whereby, at least in this sort of chair conformation here, as is drawn, again, the two methyl groups are sort of on opposite sides of this sort of pseudo ring. So if we were to sort of look at this molecule from the top down, if we wanted to give a different perspective of this, first of all, even though Margot said it doesn't matter, what would be the stereochemistry of the enol, even though it doesn't matter? Right, it would be trans. Again, you can see it because this is trans now, right? It's sort of gone from equatorial to now sort of pseudo-equatorial. So we might as well, just to be complete, we'll draw that there. Okay. Now, if we're looking down at this molecule, right, if what we're looking at is this carbon here, right, if we're looking down at it, this methyl group, is that going to be coming towards you or away from you? It's coming towards you, right? It's the first one as you're sort of looking down, you get to the methyl group before you get to the proton. So it's the methyl group that comes first. Okay? And then on the other side, as you're looking down, right, it's the proton that you see first. Right? So as you're sort of looking down, the proton comes first, followed by this sort of methyl group. Okay? So again, as it's sort of drawn here, what you end up having is the two groups opposite of one another. And again, if you're struggling to see this, just think about it, just think about it as your standard chair, right? If you guys spend a lot of time, it's really no different. You throw a little bit of a change in something, and I get that it can sort of right? But if you sort of think about this as just a sort of standard chair question, right? And I was to ask you to draw this molecule over here, you do the same thing, right? You would basically look at this molecule and you'd say, okay, this methyl group is going back, right? And this methyl group is coming forward. It's the same kind of concept. It's just that we've now, instead of drawing a 6-membered carbocycle, we're sort of drawing this transition state, which happens to be in the chair conformation. Okay? And again, this is going to undergo the enol keto tautomerization, but certainly if this was a question like the one on the exam, right, this is where it might be a little bit different between these two transition states, because if we went through this transition state, right, what would it be if we went through this transition state? Right, this would be now cis. So that's the big difference, but in the case of the question that we asked, it doesn't really matter. Yes. So let's go through it. Let's again. This wasn't the point that I wanted to make, but we'll do it really quickly. If we go through the transition state here, this would be your methyl group here, and I'll just say it back in a second. And over here we would have methyl group. Okay, so this would be the transition state here. Okay, so as you'll notice, this would be the product here, right? And so you'll notice that in this case, if we do the same thing, right? We've switched to which comes first, right? Like if we're looking down. So I guess it's also kind of different in enantiomer, but if we're looking from the top face, right, this methyl group is going to hit you before the proton does. Over here, right, and on the other one, the proton's going to hit you first, so the methyl group will be back. Bless you. actually, this became a pretty cool question in retrospect. I'll get to this in a second. So there's something important about this reaction. So anyway, so this one right here, right? That's going to be here, but you see how it's going to be now cis, right? But that's kind of irrelevant. But there's something else really important between these two. What is it? Nope. They're enantiomers, right? So this is kind of neat, right? Because what it tells you is that the stereochemistry here, isn't that kind of neat? You're like, it's not that neat. No, it's pretty cool, right? So you've got a set stereochemistry. This would be a great exam question. Maybe. For next year. Or maybe this. No, but you see how, so depending upon what our stereochemistry is here, right, the sort of relative stereochemistry here versus here is different. The products are the relative, they're the same, it's the same diastereomer in both cases. But you can see that this versus this, it's methyl coming towards you versus methyl going away from you. And over here, it's methyl going away from you versus methyl going towards you. So if you were going to try to make a molecule such as, say, this one right here, with as the major enantiomer in some process, you can imagine starting with a molecule like this. And perhaps what you could use is maybe to make it even bulkier, maybe you put like a big PBS group over here or something like that, right, to get it really bulky. And then maybe once you get to the enol ether, it falls off something. So that was kind of neat, because there is a difference. I just didn't recognize it until I physically drew them both out. But they certainly would be enantiomers of one another. In addition to the simple, but we don't really, in this class, we really haven't addressed enantiomers too much, but that's kind of neat. Yes, Mark?
So the third one you did there, only why bond involved in this. I remember how long the one when we did share stuff, I thought everything that was destroyed would become active, everything that active become destroyed.
So this is not,
It doesn't work here because the double bond is something?
because it's not a, right, because, well, what can you do, right? This isn't locked. This isn't a locked bond.
Right, I mean, because I remember the situation.
Yes. Previously, what we learned is that when you do a chair flip, right, that will happen. But this is pseudo chairs. These aren't full-blown chairs. And you're right, because the alkenes there, you're simply rotating around this bond effectively, right? And that's becoming this one over there. So it's not a full-blown chair flip. You're just trying to rationalize it as a chair flip because that's what you're comfortable doing in the past. But yeah, there's an alkene there. You're not going to. This bond here is not. It's not locked like it is in a normal chair, right? That's not a bond. So you're going to rotate when you do this. You're going to rotate around this bond and you're going to rotate around that bond, which you could not do in a regular chair. Got it?
I was confused with why the method was still staying at equatorial position.
Right. Right. Wait, what? No.
Because I drew it and it was both axial, so like everything changed.
No.
Not because I drew it like split, but that wasn't missing.
This is the same molecule as this.
How can you do the same?
It's not the enantiomer. It's the same molecule, but the product is an enantiomer. That's what I was saying. There's a stereo center over here, and that's the point that I'm trying to make. Is depending upon which transition state you go through, one will lead to one enantiomer, the other will lead to the other enantiomer, which effectively comes back to I think what Mark was sort of confused about, because you can't just make a new chair enantiomer, right? But because what we're dealing with is transition states, and because of the fact that you've got a bond there that you can break, right? So you can rotate around this bond here, and this one you can break and rotate around that bond there. These are things that you cannot do in a chair, right? And at the same extent, you have to stay locked into that alkene. Okay, one question, Vince, and then we got to move on.
Yeah, so my question is, can they still be enantiomer if one is dense and one is thick? Because like the left one is thick,
Probably.
the right one is
Try it.
dense.
Try it at home. And everybody else can try it at home too. Try that out. Okay? All right, so, and then just see what you get. So just take it through it and answer that question. So the question that Vince asked, and you can all email him once he figures it out. No, but I think it's a good question. It's a good practice just to follow up on this one to sort of make sure that you can do it. All right, so you got a half hour. I was asked to also do some synthesis questions. So we'll do a couple synthesis questions. Huh? That you guys were supposed to. Well, that was the reason I told you guys to email me in advance so that I could. If I have time, then yes. Okay, so I got a couple emails about synthesis questions. One, somebody said, "Can I get a really hard synthesis question?" I can't spend time in a really hard synthesis question here, but I'll just do a sort of a few step synthesis question based upon what somebody else asked. And the sort of question is. Starting from this molecule, can you make, can you make that molecule there? So that's synthesis question number one. And again, you can use any other source of carbon, but it's going to use, the most efficient way I think to be able to do this is going to certainly use enolate-based chemistry, so really consider enolate chemistry, and I think if you do that, this should actually be a really, actually super easy question. The other question that I'll put up there is, now I'm thinking that was too easy actually. And so there's another synthesis question. So we'll start with this one, okay? And I think I've drawn the first synthesis question in a way that's kind of perhaps suggestive of what the answer could otherwise be, okay? And I think that when you're considering and contemplating synthesis problems, one of the really, I think what your inclination is to do as a second semester organic chemistry student is to sort of think forward, right? I think a lot of people have really struggled or they've been very reluctant to think about retrosynthesis. And certainly retrosynthesis can really simplify compounds fairly readily and efficiently and make answers perhaps much more clear than they would otherwise be. So I would urge you all to really consider if there's a synthesis problem on the exam. Think about retrosynthetic analysis. Think about what are some of the molecules there, what they could otherwise be, and then look at some of those products and see if perhaps any of those suggest a much clearer sort of finish line to the finish line. Okay? Now, when you sort of look at this molecule in general, there's no right or wrong way to really do synthesis. Again, that's why it's sort of all about practice and getting comfortable and doing different things and figuring out on your own. But when you see a molecule like this, do you sort of notice anything? And again, perhaps it's a little suggestive, but what you sort of see in here is perhaps the remnants of that molecule right there. And the reason why I perhaps put this here rather than here or here, well, that would be difficult over there, but certainly based upon here, is what? Is that I have a certain oxidation state here that closely resembles the one that I have here, right? And so changing of oxidation states can often be one of the things that takes a little bit of time. And so if you're thinking about making this molecule, and it's not that you couldn't make this, right? It's not that you couldn't make this, right, this one here, but then what you're left with eventually is that you're probably going to then have a ketone there, and then you'll have to do a Wolff-Kishner. But, which isn't the worst thing in the world, but I think there's another advantage here, and that's that you guys know a really good way to take a ketone into an alkene, and that's going to be the Wittig olefinations, right? So if we think about a Wittig olefinations, right, and we do a retrosynthetic analysis from here, right, what we recognize is that we effectively have our ketone, right? Right? So how do we, what's the reagent for a Wittig olefinations? Right? So you can draw it as a salt, or you can draw it as the illid, or whatever. But then when you're here, if you remember another reaction, we're basically a step away. Yeah, it's going to be an aldol reaction, right? So if we take this molecule, what we see is that it's this bond that we have to break, right? And that should be another retron that you recognize very readily as being sort of aldol reaction, exactly. So just to sort of remind you guys, right? The first step is going to be LDA, some strong base, right? So let's say diisopropylamine, right? That's going to get to the enolate. Exactly. And then what we're going to do is treat it with formaldehyde, right? Which is going to lead to the alkoxide, right? And then, so we're going to quench it with water. And that's going to get to the product, right? So, so again, you know, this is probably super easy synthesis problem, but it might not have been. Like, I guarantee that if I put this question and maybe redrew this a little bit different, maybe rotated the double bond around or something like this, some of you guys would come up with like 20-step syntheses of this reaction. That's fine. If you can get there, that's fine. But the point is, you don't want to be spending too much time on an exam on a synthesis problem. It's worth it to really take a step back, evaluate it, and really think if there's some way that you might simplify it that might make the problem a lot faster. Okay. Now here's one that I sort of thought of this morning. How might we, we've talked about making peptides, how might we consider making sort of a cyclic peptide, right? Yeah, what? Right? That's a good point. Maybe we can just take this and treat it with DCC and we get some of this, right? Like, yeah, maybe. But I'd rather a more controlled way to do it. But you're right, that we would want that process, but when would that final process take place? Probably, oh, sorry guys, I'm sorry. That's what I meant to do. The final step is going to be the peptide cyclizing, right? And so, wherever we want to do it, we can sort of draw that retron, and what we see is that if we consider this as just being a peptide coupling, but a cycle addition, like a peptide cyclizing on itself, then what we have here this molecule here, and we'll cyclize it simply with DCC, right? So we'll take this compound, and we'll treat it with DCC. And again, some of you might say, well, can we really control this? Because maybe we get polymers and stuff, but that's one of the nice things about intramolecular reactions, right? Is that when you have an intramolecular process, it will certainly be much faster in general than an intermolecular process. And the other thing about it is that the nice thing about molecular processes, you always make the reaction really dilute, right? So you limit the ability of the molecule to react with another version of itself by keeping the concentrations really low. So intramolecular reactions are very easy to do. Or I shouldn't say that, but you know, they're generally easier than their intermolecular counterparts. Okay, so at this point we have this molecule, and we don't want to just go straight to another DCC coupling, right? Because the chances are is that that's going to be a mess, right? As we sort of stated earlier, we're probably going to want to have some control. But sort of looking at this from a retrosynthetic standpoint, we can recognize that both of those can be deprotected at the same time. So if we want, we can choose protecting groups that are going to be deprotected under comparable conditions, right? So whatever those are going to be, right? We can imagine. Holly, give me a type of protecting group. Bach. Okay. And so Bach is for which one? No. Holly, for is it an amine or the carboxylic acid? For the amine. Okay. So we're going to put the Bach group on there. And then what then would be our acid protecting group? If this... No, we said we can be protecting at the same time. Yeah, I mean, or you can just look at what's being deprotected over here, just put that, right? Yeah, just put the T-butyl group over there, right? I mean, again, the only one where you really have to get creative and remember is when we start getting the base deprotected ones, because you generally don't put FMOC on a carboxyl, the FMOC type group here. But yeah, in the case of a Bach group, that's why it's worth it to not memorize the name, just get the structure, because this group is the same as this group, and if you sort of understand the mechanism, then you should understand how they're both deprotected. And so, rather than trying to necessarily remember the name, although the name's good to know, if you know, given a choice, if you're going to know either the name or the structure, definitely know the structure. And in this case, it would help relate them, okay? And now with these two components, again, we can deprotect them with what? Some acid, let's say trichloroacetic acid, right? Okay, and then we can break these up into individual components. Okay, so it's going to be that guy, as well as, and so it just becomes a game of protecting groups at this point in terms of putting on the appropriate protecting groups. All right, because if we want to do this, it's simply DCC again, okay? Right, and so now the question becomes, how do we put these groups on there? Right, in the case of this compound here, you should be able to put it on simply by taking it and treating it with Bach anhydride. And that would be phenylalanine. I'll just put starting material. And this one might be a little bit trickier. How might you imagine protecting the sort of T-butyl group? Like, there's sort of conditions, I think your book might even mention one of them, because I got an email from somebody about like basic type conditions that can get to this. I'm not too familiar with them at that standpoint. If I were going to be doing this, well, first of all, the nice thing is that you can generally buy all the different protected amino acid starting materials that you want. I'm sure there are conditions out there that can be used to selectively protect this, but if you wanted to be safe, right, because the amine is generally more nucleophilic, so especially with the T-butyl protecting group, what I would probably do, just to be safe, is you may want to protect the amine and then deprotect the amine afterwards, right? So do orthogonal protecting group here. Again, I think that you can use like, I don't know, I think that there are conditions that you can use to selectively put that on there. But certainly what you could do is have an orthogonal group, right? Where, say for example, Holly, give me another protecting group for an amine. FMOC. Right, so if we put the FMOC group on there, right, because we can deprotect the FMOC with just piperidine, right? And again, we can put on the T-butyl, the T-butoxide in the presence of the FMOC groups. I'll just FMOC. Again, I think the conditions that the book gives you guys are acid and sometimes it's acid and that, right? And that will take you from the carboxylic acid, right? And then certainly the FMOC you can probably put on the starting material using FMOC fluoride. Okay? So this is just a way that you would cyclize, get a sort of cyclic peptide, yes?
Just out of curiosity, if you ask this mechanism for mass acid, would you have to do that first step with the FMOC protection, and then add on the and then...
Well, let me ask you, how would you do it?
No, I'm thinking the way you put it beforehand, which is like sort of throw protection onto the power, throw a...
Well, we kind of did, except that we discussed that it may be difficult to throw on a T-butyl group, right? Because of the generally acidic conditions that you use to put them on. If you have another acid-sensitive group nearby. Yeah, I mean, I'm not sure. I don't know if you can just put this on in the presence of the amine. I should probably know that. I think to be safe, just put the protecting groups on there. I can't guarantee. It's probably going to depend on the mood that I'm in. And I don't want to tell you guys to not because you're going to want to make sure that it's a reaction that's going to be selective. And so if you have an amine, I guess the rule of thumb would be, this is what I would tell you guys. And again, this isn't necessarily always the case, but what I want you guys to do when you're talking about orthogonally protecting groups is go through one of two methods. Okay, so I'll give you this guideline, and as long as you follow this, you can do the selective protection. Hold on a second. 1 second, Ken. So what I would say is this. And again, it's not as simple as this, but I think at least in terms of getting you guys to think about orthogonal chemistry, it's at least it's a good enough of a mental practice to sort of consider this. Whether or not this would actually translate into the lab is another story. But again, when you're in the lab, you can look up the conditions. So it's better that you sort of understand the general concept in my opinion. But if I gave you a question like this and I asked you to treat it with some electrophile, which one would you expect it to go after first? I would expect it to go after the amine. Again, the carboxylic acid is kind of interesting in a way because it does have that resonance stabilization by attacking the carbonyl. But I think it's fair enough to assume that the amine might be nucleophilic enough, at least we can consider it for the exam in a couple days, to say that the amine is generally going to be more nucleophilic. Now, if we want to make the carboxylic acid more nucleophilic, we can do that as well. But we want to do it under slightly basic conditions. Right, so I would say that for the exam, just sort of consider this. That as long as you treat it with a mild base, you can get to the carboxylate. And if you're at the carboxylate now, the oxygen is a better nucleophile. And again, I'm not sure this is 100% accurate, but I think for what how I want you guys to sort of think about synthesis, just recognize that there could be conditions to choose between the two. So, Felix, yeah.
I was thinking that if the option is like twice and if the option is like one less time, then the rest of maximum.
That's what what I was saying is that this carbonyl might actually be a better nucleophile in principle. I'm not sure if that's the case necessarily, so what I'm telling you is that for the sake of selective protecting within the context of the exam in a couple days, to sort of get you guys thinking about the complementary nature, whether or not this would be 100% accurate or not, would just be to say that if it's in its neutral form, consider the nitrogen to be the better nucleophile. In its deprotonated form, consider the carboxylic acid to be the better form. Now, whether you want to agree with me on that or not is another matter. The truth of the matter is that, again, you can always look up the conditions if you were actually in a lab. And so it's more important, in my mind, to sort of recognize that you can attenuate the relative nucleophilicity of the two. And that would be the sort of way that I would go about it. Kevin?
My question was about the relations that you'll use the relation after.
Right.
When you protect the carboxyl.
Mm-hmm.
Can you just even ask Fisher's verification in this case because so that you're using the tertiary alcohol?
So I guess then the other question is if I'm under acidic enough conditions, really acidic. I guess this is the other option, right? Maybe that's what you're saying, right? So now I've kind of protected the nitrogen as a carboxylic acid. So just sort of use your judgment. And I think that's what you're saying, is that if you're under really acidic conditions, maybe you can do it. And maybe even under these conditions that I outlined here, maybe you'd be okay. Because maybe what's going to happen is under these really acidic conditions, you're not going to react with the amine because the amine is going to be existing as the ammonium. So again, just do your best. Do something that's, don't just treat it with some random electrophile. Sort of consider these guiding principles. If you want to go under acidic conditions, and you're sort of concerned and you're sort of thinking about that, just bracket that that's what you're thinking, right? Just put, this is my reactive intermediate. If there's any selectivity issues that you might be concerned about, and at least I'll know that you're thinking along the right way. Yes, Margo?
I was wondering, this is the whole ethanol and, having nitrogen and doing the search for the topic.
Yes.
Why don't you just do a diazomethane and either switch up
Sure.
the acid and
Sure.
then
Sure.
sulfuric acid to the CFA acid, keep the pressure, it's a constant anyway.
So what Margo's saying is, I see what you're saying. So instead of having a T-butyl protecting group, Margo's saying, well, we know that we can do hydrolysis of esters. So, what's that? Yeah, sure. Yeah, so Margo's point is that we put a T-butyl group over here. Why don't we just put the methyl group? And that way, under aqueous acidic conditions, if we're going to deprotect, say, the Bach under aqueous acidic conditions, well, we'll likely hydrolyze this as well. Perfect. Right? Because you can hydrolyze methyl esters under either acidic or basic conditions. Now, what you're not going to deprotect this under is like TFA.
Right, so sulfuric acid.
Water? Sure.
Acid.
Well, yeah, I think you're fine. Just stick with, because at a certain point, you're going to start, under those strongly acidic conditions, you're going to start actually hydrolyzing the amide in reality. But I think that's fine. I think if your point is I want to go to, aqueous acidic conditions that I know will hydrolyze this will also take off the Bach group. And certainly the Bach group's going to come off under those conditions. And certainly you'll be able to identify conditions, aqueous acidic conditions, where you'll be able to take this off in the presence of an amide. Amides are much stronger bonds to hydrolyze, so it would be much harder. And so you would be able to do an ester in the presence of an amide. Whether boiling sulfuric acid, that's probably not going to work. But there will be some aqueous acidic conditions where you could do it. Jamal?
The way you have it,
Yeah,
the
sure.
way you wrote it down.
Okay, so in the last few minutes, what we'll do, we'll just discuss end degradation. to, okay, so the end of degradation, we're basically going to take phenyl isothiocyanate, we're going to treat it with an amino, some sort of peptide. So again, this will be our sort of peptide over here. But the important point is what we're going to do here is the isothiocyanate is going to react readily with the amide. That's effectively going to create an internal nucleophile that's going to help hydrolyze this overall system, right? So again, the first step in this reaction is going to be attacking the carbon. Again, you can push the electrons this way, or you can push them this way. Eventually, those electrons are going to end up probably on the nitrogen, following and then we'll probably get a proton transporter here, right? So. Okay, so what Jamoke is saying is that at this point we're going to effectively do a hydrolytic, catalytic hydrolysis. And there's a couple different ways that you can do this. The product that you form is this. Is effectively going to be the hydantoin. So the nitrogen is going to attack, you're going to go up, you're going to come back down, and you're going to kick off. Now, I think what Jamoke is saying is that, or what Jamoke has noticed, is that that's not the mechanism that the book has. Okay? The book certainly discusses the sulfur adding first, okay, followed by a rearrangement. If you want to go through the sulfur, go through the sulfur. I think the most important point that I'm trying to make in there is that I think this is tit for tat. I think that, especially when you're considering rearrangements and so forth, certainly this is going to be more nucleophilic. So if it's really bothering you and you're saying, this is more nucleophilic, and you really want to add with this, that's fine. But what I've often told you guys is that in mechanism questions, sometimes you have to give yourself a little bit of flexibility. And so if you were to say that this nitrogen is more nucleophilic, and here's the bottom line, that's a reversible process. Okay, once you're ultimately going to cleave that is going to be a reversible process. The nitrogen will effectively come around and react at that center. So I don't really care how you do it. You can do it either way. This is more direct. But the important point is that you sort of get to this hydantoin product. Right, so you're effectively going to get that hydantoin. So you can add through the sulfur if you want and do the rearrangement, or you can add through the nitrogen. I really don't care. Yeah? Yeah. So in this case, I just had glycine, right? And so glycine wouldn't have anything here. So so you'd basically, you'd look at this, you'd figure it out, and you'd know that that was your first N-terminus. Then you move on to the next one, you figure out the next N-terminuses. Then you move on to the next one, you figure out the next, just based upon the mass of this plus, because they're going to vary based upon the appendage, and that appendage is going to tell you what amino acids there. Yeah?
How does it work with other what molecule, what's one compound of that each one that comes off?
Yeah, so you start, it's iterative, right? So I've never done degradation, but my guess is that you first treat this molecule with the peptide. It reacts fully, and then what you probably do to initiate this cleavage is you probably then heat it or something afterwards. I don't know, it depends on what I ask you. You should just recognize this process. You should recognize that this reagent can be used to cleave the N-terminal amino acid. Well, now you have a nitrogen. It's the same thing as here, but now you're at the next amino acid. And now you'll get a new compound like this that would represent the other, the next amino acid. Yes. Yeah. So it's like a series of reactions. It's like analyze the N-terminus. Okay, now there's a new N-terminus because so what's the next one? Okay, now what's the next one? And same thing, yeah. Okay? All right, guys, Monday morning, be here bright and early.
Monday?
Sorry, Wednesday morning, be here bright and early.